In this video, we're going to see how to find the roots of complex numbers. We're going to do two examples, z cubed equals 1 and z to the power 4 is equal to minus 2 plus 2i root 3. So starting with z cubed equals to 1. Now on this slide, I've shown how to do this the long way, as if we were in year 12. This is just so I can show you what the three solutions are. In a moment, I'm going to show you what the shortcut is, so you won't have to do this long method. But what I've done here is z cubed equals 1. We're expecting to get three solutions because it's a cubic equation. And I know one solution, obviously. I know 1 cubed equals 1. So I know 1 is one solution to that equation. Which tells me that z minus 1 has to be a factor of z cubed minus 1 equals 0. So I've just done some algebraic division over here to work out what the quadratic factor that goes along with that is. I've then solved the equation to work out the other two solutions by completing the square. You could use quadratic formula if you prefer. So the three solutions to z cubed equals 1 are 1, minus a half plus root 3 over 2i, or minus a half minus root 3 over 2i. Now let's have a look at the shortcut. So, the shortcut will be more obvious if we're working in exponential form. You can do it in Cartesian form, and you will do it in Cartesian form, but it is much easier to show you and do it in exponential form if we can. So first thing I want to do is to rewrite my answers in exponential form. So the 1, that's obviously just going to be 1. We don't have to write that in a different form. But the minus half plus root 3 over 2i, let's write that in modulus argument form. So let me just take that. I know this is a half, I know this is root 3 over 2. So a little bit of Pythagoras there tells me that the modulus of this number is 1. So 1e to the I. Now to work out its argument, if I call that angle there alpha, I can say that tan alpha is equal to root 3 over 2 divided by a half, which is root 3. Tan inverse of root 3 is pi over 3. So alpha is pi over 3. So therefore the argument here would be pi take away pi over 3, which is 2 pi over 3. Now that should hopefully make sense, because hopefully it's actually pretty obvious that the angle is going to be 2 pi over 3. And also this angle here is also going to be 2 pi over 3. And this angle also is going to be 2 pi over 3. Because we've got 2 pi radians in total, and we've just split that into 3 angles. So hopefully that's pretty obvious. And from there we can work out the argument of z3 pretty easily as well. You could do it the long way I just did, or we could just look at our diagram and say the argument's going to be minus 2 pi over 3. So I could say that z3, its modulus is going to be 1 again. Again, to do a bit of Pythagoras there if you want to show that. E to the minus 2 pi I over 3. I could also say that the argument is 4 pi over 3. It's a bit unusual to do that, but I'm actually going to do that here because it's going to help me to show the shortcut a bit easier. So I've got my three solutions in exponential form. Here's the shortcut. I've got my first solution, which is 1. and I've multiplied it by e to the 2 pi I over 3 to get the second solution. And then to get the third solution, I've multiplied the second solution by e to the 2 pi I over 3. Remember that when we multiply complex numbers, we add their arguments. So if I add these arguments, I get my new argument. Geometrically, adding the arguments, increasing the angle, causes a rotation. So multiplying by 2 pi over 3 means adding 2 pi over 3 to the argument, so rotating by 2 pi over 3. Then multiplying again gives me another rotation of 2 pi over 3. And then multiplying one more time gives me another rotation of 2 pi over 3. Why 2 pi over 3? Well, there's 2 pi radians in total, and we were expecting 3 solutions to be evenly distributed. So 2 pi divided by 3. Generally, if there are n solutions, I would expect 2 pi over n to be the angle in between each of those solutions. So I would multiply by e to the 2 pi I over n. Sometimes we call that factor that we multiplied by either w or omega. But the idea is that we find our first solution, whatever that is, and then multiply by this w factor. So let's now apply that shortcut to a slightly harder question, which is this one. We've got z to the power 4 is equal to minus 2 plus 2i root 3. Now, I don't know what the first solution to this is yet. We'll work that out in a minute. But I know that once I've got the first solution, I can multiply it by e to the 2 pi I over 4, because I know I'm expecting 4 solutions because of the z to the power 4. So I know I'm going to have the 2 pi split between 4 different solutions. So I want to rotate 2 pi over 4. So how can we find that first solution? Well, I want to be working in exponential form. So you can see just over here, I have taken the minus 2 plus 2i root 3, and I've written that to work out its modulus as being 4 and its argument as being 2 pi over 3. And I want to find my first solution, z1, where I put it to a power 4 and get that answer. So let me rewrite z1 as re to the I theta. So we've got r to the power 4, and then e to the I theta times 4 is 4i theta. Now comparing, I've got r to the power 4 equals 4, which means if I square root it, I get r squared is equal to 2. Square root again, so r is root 2. So I know the modulus of z1 is root 2. Now comparing the powers, I've got 4 theta is equal to 2 pi over 3. So therefore, divide both sides by 4, I get that the argument is pi over 6. So my first solution to this z1 is root 2 e to the pi I over 6. That's my first solution. And now I've got my first solution, I can use my shortcut to get the other solutions. So all I need to do is take the first solution I've just found and multiply it by the e to the 2 pi I over 4. Remember, multiplying means we're just going to add the arguments. So the pi over 6 plus pi over 2 gives me the 2 pi over 3. Multiplying again to get the third solution, again means just adding the arguments. So I get 7 pi over 6. And then multiplying one more time for the fourth solution. So again, add the arguments together, and we get 5 pi over 3. And then all I've done at the bottom down here is written these out again, just making sure that my angles are between pi and minus pi. So the 7 pi over 6 is the same thing as minus 5 pi I over 6. And the 5 pi over 3 there is the same thing as minus pi I over 3. And if you wanted to, you could. So I've got all my answers here. I've solved it in exponential form. If you wanted to turn these back into Cartesian form, then we could just rewrite this as root 2 cos pi over 6 plus I sine pi over 6. So root 2 cos pi over 6 is root 3 over 2. Sine pi over 6 is a half. And so multiplying that, then we get root 6 over 2, excuse me, plus I root 2 over 2. And if you want to check that, put that to the power 4, and you will get this. So that is how we can find the roots of complex numbers pretty quickly. Geometrically, the results there look like this. The modulus of each of these numbers is root 2. The argument of the first number is pi over 6. The argument of the second number is 2 pi over 3. The argument of the third number is minus 5 pi over 6. The argument of the fourth number is minus pi over 3. Or, another way of thinking about it is we know this is root 2. We know that this is pi over 2 because we rotated by pi over 2 each time. Or again, you've got your 2 pi radians divided by 4. Two other things to say. You'll have noticed that in both of these examples we've done, we've ended up with regular polygons centered on the origin. The z cubed equals 3 gave a regular triangle where each of these is 2 pi over 3. We knew that each of these lengths was 1. So if we wanted to, we could do a bit of cosine rule to work out the lengths of these sides here. So we got a regular triangle. Similarly, with the z to the power 4 equals minus 2 plus 2i root 3, we got 4 solutions that formed a square. We knew each of these was root 2. We knew each of these angles here was a right angle. And again, we could work out, do a bit of cosine rule, a bit of trigonometry or Pythagoras to work out the lengths here if we wanted to. Other thing to note at this stage is when our z cubed equals 1, this is called the roots of unity when it equals 1 as opposed to something else. In the case where it's 1, our first solution is on the real axis. In the case where it's not 1, our first solution is not on the real axis. We've got a little bit of rotation at the beginning there. Final thing to say, the sum of each of the roots. Now I could do this manually. Remember that z1 was 1, z2 was minus a half plus root 3 over 2i, and z3 was minus a half minus root 3 over 2i. And notice that the 1 minus a half is 0. And the root 3 over 2i minus root 3 over 2i is also 0. So the sum of those roots adds up to 0. And that's actually always going to be the case. And you don't need to do that the long way I just did. You could think of each of these complex numbers as vectors. If I did vector z1 and then added vector z2 to that, and z2 looks like that, so if I add that to z1, I do that, and then if I add vector z3, notice I do get back to the origin. It equals 0. Similarly, with the z to the power 4 solution, if I start by adding vector z1 and then add vector z2 to that, I get to here. Then if I add vector z3 to that, I get to here. And then if I add vector z4 to that, again, I get back to the origin. So the sum of those roots is equal to 0. And as I say, that is always going to be the case. So a couple of useful geometric things to think about there at the end, and we're going to talk more about those in the next video. But key thing really, I think, is remembering the shortcut of how to find the roots of complex numbers. Find the first solution by doing the modulus, getting it in exponential form like that. And once you've got your first solution, multiply it by the e to the 2 pi I over n, where n is however many roots you're expecting to get.